Alright, so today what we're going to be looking at, switching gears a little bit, is we're going to be looking at what's called the limit of a function. Now in advanced functions, I did anyways, we did look at limits, especially when we're talking about vertical asymptotes. It's going to be a little bit different today because we're going to start with the basic limits. And to start off, example 1 here, we have find the limit. And so this time we have the limit as x approaches 3 and our function here is 4x minus 2. Now before, when we were finding the slope of a tangent and we were using the definition of first principles to find the slope of a tangent using the limit, we had an issue with subbing in 0 in for h because our denominator was 0 and you can't divide by 0. But in this case, I look here and there's actually no fraction, and so I don't have to worry about this when I substitute in the function being undefined, as we say. And so I can actually plug a 3 in here for x, so 4 times 3, which is 12, and then I subtract 2. And so I can just straight substitute in, no problem. I get to b here, where I'm looking at the limit of our function right here of 1 over x plus 3, and I want to know what happens as x approaches 4. Well, this time I do have a denominator. But when I substitute in a 4 here, there's no issue. I can divide by, well, 4 plus 3 is 7. I can divide by 7. And so I can substitute that in, and I get 1/7. Alright, so C. I've got a quadratic equation where I have 3x squared plus 4x minus 1. And I want to know what that function is as x approaches 2. But again, I have no denominator to worry about, so there's no problem here. I can substitute in. And so this one's a little bit longer, so let's see here. I got substitute in a 2, so I got 3 times 2 squared plus 4 times 2 minus 1. Well, let's see here. I got Badness, got to follow Badness. 2 squared is 4 times 3 is a 12. Plus 4 times 2, which is an 8, minus a 1. And so, let's see, 12 and 8 is 20 minus 1. This limit would be 19. Alright. Now, we get to D. A little bit different. We have our function. We do have a denominator this time, because our function is x squared minus 25 divided by x minus 5. That nice darker words there. There we go. Now we're looking as x approaches 5 into that function. Now you look, what happens is that if I plug a 5 into my denominator, I do get a 0. Problem, because I can't divide by 0. But I got a way out of this. Is because what I can do is I can actually simplify this function. And so on the top there I have x squared minus 25. Well, that is a difference of squares. So I can factor that, because if it's a difference of squares, first of all you're going to have 2 brackets. And again, I'm not going to do anything with the bottom here. And so let's see here. Difference of squares, one's a plus, one's a minus. Square root of x squared is x, so that's the first one, goes in the first spot. The square root of 25 is 5, so 5 goes in the second spot. And now if I look for our limit here, I've got x minus 5's that will divide each other out. And so I'm looking at the limit as x approaches 5 of x plus 5. And so because I factored that numerator and was able to divide out a piece of the numerator and the denominator, I can now substitute in my limit, because just like we did with finding the slope of a tangent and being able to factor out an h and then divide the h's out, I can now substitute in. And so if I put a 5 in for x and I add 5, my limit would just be 10. Alright, now, something that happens at that function, this function here, is that 5 is a spot where there is a bit of a problem. And we're going to look at that problem, but in a future class, I think next class, but it's called point discontinuity. And again, that is something we are going to talk about in our either our next class or the class after that. So even though we can find that limit, there's something that goes on there, and you're actually going to see something like that in an example coming our way. Now, these are kind of what I call straightforward limits, where we can just substitute in a value and no big deal. But there is a rule for all limits, but we're going to look at special ones. So for a limit to exist, which is what we call L, so it's number. So L here would be 10, L here would be 1/7, our limit here would be 19, and our limit here would be 10. So if you have a limit, if you have one, we have as x approaches some number a, and this negative sign means from the left-hand side, is equal to that same limit as we approach that number from a plus sign, which means from the right-hand side. Now that is something I did go through in advanced functions, and we're going to go through it again, what the left-hand side and the right-hand side mean. But if your left-handed limit and your right-handed limit are the same, then you actually have a limit. Otherwise, it doesn't exist. So not all the time do you actually have a limit. Sometimes it just doesn't happen. It doesn't exist. All right, so that again is our rule here that we're going to be looking at in our next few examples. Your left-handed limit has to equal your right-handed limit. If not, it doesn't exist. All right, so what does that mean? Right? So flip it over here. And so this is where I'm going to try something a little bit new here because Google Meets has stopped letting me record. So I don't have nice graphs like I used to. All right, so tighten that up. There we go. All right, so here we go. Example 2. All right, I actually have a graph there. And it says, and I'll write it out because I'm not sure how close or how well you can see it, but it says find the limit as x approaches 3 for our function. All right, now what I need to do is, first of all, look at the limit, the left-handed limit. So as the limit approaches 3 from the left-hand side, and I also need to look at the limit, I guess I'll write it over here, as x approaches 3 from the right-hand side. All right, now if those two things are equal, then our limit is going to be that number we came up with. If they're different numbers, then the limit does not exist. So, what does this mean? As x approaches the limit from 3 from the left-hand side. Now I'll tell you here, I'm not sure if you can see it on my graph. I know you can actually. There's the x value of 3 right there. Now as I approach 3 from the left-hand side, so I'm coming from the left here, so I start at my arrow, I move up and 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 up. And now as I get to 3, because there's actually a hole there, you can kind of see it on your camera. But as we get to 3, we don't get to 3, but we're approaching it 3. That's what that arrow means. The value is, it's got a height of 2. So the limit is 2, or the left-hand side limit is 2. And now I'm going to look at the right-hand limit. So I'm coming towards 3 here, but from the right-hand side now. And so I've got a curve here, and it goes down, it goes down, it goes down, it goes down, it goes down. And again, as we get to 3, as we approach 3, it has a height of 2. And so because our left-hand limit and our right-hand limit are the same, therefore, the limit as x approaches 3 of that function that we have here, it's going to equal 2. All right, now, just like I had in our last example where I said something special goes on, where there's a hole, well, that would be point discontinuity, what we have here. Our function goes along, but then there's a hole there because it jumps up. All right, so that is called, again, we're going to talk about discontinuity in a future class. All right, now, let's see here. I got my next function. So we'll do a little bit of cleaning. All right, so our next one here. All right, so here's our next one. Whoa, crooked. There's that. And there's that. All right, so this one, whoops, getting tape stuck to me here. All right, so this one says draw f of x and find the limit as x approaches 1 of f of x. All right, so I have to draw this function. Now, where our definition of looking at the left hand and right side limits come from is the fact that a lot of times it applies to what's called piecewise functions, where your function's actually broken up into pieces. And so this one here is talking about as x minus 1 when x is less than 1. So I'm going to graph that piece of our function. It's going to need a paper marker. All right, so I'm going to have x equals 1 right here. Now it says at x minus 1, or the function less than 1 is x minus 1. So that is a linear equation. All right, so if I plug in 1, well, 1 minus 1 is 0. So I guess I'll put a big circle there because it's not exactly, it's not 1 right on because it's x less than 1, but I do plug in a 1. And then what I have is a linear line with a slope of 1 from there. So it's a linear equation. Let's draw the rest of the axis. Now it says at x equals 1, the value is just 1. Okay, so I'm going to plot that. That's just a point. There we go. So I put my point in there. And again, that's at a height of 1. Then it says for x greater than 1, your function is a square root. It's at the square root of x minus 2. So let's see here. I plug in, let's see, 2. A 2 would even be 0. Because I can't even plug a 1 in, it would be minus 1, and you can't take the square root of a negative number. And so what I'd be looking at is, say, like plug in a 2 and I get 0. So, let's see, plug in 2, you get 0 right here. And then our function would go, whoops, just like that. All right, so now I want to find the limit. All right, so let's see here. Okay, so if I have my limit, oh, I wrote it down wrong. I thought I did. That should be a 1 there. So I can put an x equals 1 in there, and I actually get 0. Let's see here, hold on here. Put a 1 in, I get a 0. I think I wrote this down wrong. Hold on here, folks. X minus 1, yep, less than 1. Ah, I did. There's a plus 2 here on the end. How did I miss that? Alright, so, man. Okay. Let's just redraw this. Oh. That's a permanent marker. We don't want that. That's bad news too. Alright, so let's draw this again. How did I mess that function up? I don't know. Early in the morning. Alright, so here's our function that we're going to draw. F of x, piecewise function. Alright, so we have x minus 1 for x is less than 1. We have 1 when x equals 1. And then I have the square root of x minus 1 plus 2. Well, that's where the 2 came from. And x is greater than 1. Alright, now, since I don't want permanent marker on my whiteboard, I better get this off real quick. man. That's not good. Alright. Sorry here, folks. This is what happens when I don't have my Google Meets. Alright, so x is greater than 1. Alright, so if I want to draw this function once again, sorry about this. Alright, we have our value of x equals 1 right here. Alright, so again, for x is less than 1, we have our function x minus 1. Again, if I plug in a 1 there, it's going to be 0. Put a line there, we got a nice linear equation. There we go. X equals 1. We have a value of 1, so it's going to be up here somewhere at 1. If I put a 1 in for x here, 1 minus 1 is 0, but then I have this plus 2. So it's going to be 2. But again, it's an open circle because it is x is greater than 1. Alright, now it is a square root function, and it's going to look something like that. Alright, there we go. Now, when I'm finding my limits, we're looking at the limit. As x approaches 1 from the left-hand side. Alright, so we got to look at our left-hand side limit. We have our limit as x approaches 1 from the right-hand side. Alright, so here's how that works. As we approach 1 from the left-hand side, so here's our line down here. We approach it, we approach it, we approach it. Now again, we don't have to be on it, but we are approaching it, and it's down here at 0. Now, we look at our right-hand limit. So we're approaching 1 from the tip of this arrow, and then we're moving downward, or I guess towards 1 from the right-hand side. We approach up here at a value of 2. We don't get to 2, but we approach 2, and so our limit is 2. And so because our left-hand limit and our right-hand limit do not equal each other, we say therefore the limit as x approaches 1 of this function that we were dealing with does not exist. And that can happen in math where we don't get an answer. There's no answer this time out. It just does not exist. Alright, now let's try another one of those. So I'm on to example 4. Whoops, I'm going to have to get rid of this stuff. My sheets are not working. Alright, so our next function, what do we got here? Let's see, scrap my sheets. Go to example 4. Make sure that's nice and dry. Alright, so example 4, we are looking for the limit, again, as x approaches 1 for our function. And our function is the piecewise function that is this. We have f of x. I'm going to make sure I write it down right this time. Piecewise function, big bracket here. We have x plus 3, and that is if x is less than 1. We have a 4 for x is equal to 1. And we have a 2x squared plus 2, ooh, quadratic, if x is greater than 1. Alright, so again I'm going to draw this function and determine if there is a limit, and if there is, what is it? Alright, so again I'm going to draw the function. Alright, so there's our, let's say our x value of 1 is right there. Alright, so for less than 1, say we have the function x plus 3. So if I plugged a 1 in there, 1 plus 3 is 4. So I would be, let's say, up here somewhere. And again, it is a linear equation, what happens if I put a 0 in there? I'd get 3, so it'd be down here somewhere. So it's going to be a linear equation. There we go. For x equals 1, we actually have 4. So that's a point. And so what happens is I'm going to fill in this point because of this right here. Because when x equals 1, well, the value is 4. And now when x is greater than 1, we have the function 2x squared plus 2. Well, I'll put a 1 in here. Let's see. 1 squared is 1. Times 2 is 2. Plus 2 is 4. Okay. What about like a 2? So 2 squared is 4. Whoa. Times 2 is 8. Plus 2 is 10. So this thing is going to go way up there. Alright. So now if I look at my limit as x approaches 1 from the left hand side, and if I look at the limit as x approaches 1 from the right hand side, we'll see if we get the same number and if it exists then. And so again, when we're going from the left hand side, I'm at the tip of my arrow, I move towards x equals 1 and well, it's 4. If I approach 1 from the right hand side, so starting from this arrow and moving down, I end up with 4. And so the limit on the left hand side is equal to the limit on the right hand side. So this limit exists. It is actually a 4. Alright, last one. Let's see, you're going to have to brush this off again. Alright, so our next one is a little bit different in that we've got conditions and we're going to have to draw it. So it says draw any function. Oh, that's too wet. Won't be able to draw nothing. Alright, so draw a function where the following are true. We have f of 5 is equal to 2. That's the first stipulation. We have the limit as x approaches 5 from the right hand side, f of x is equal to negative 2. And then our final property here is that the limit of this function approaches 5 from the left hand side and it equals 1. Alright, so there we go. So there's our conditions. Now we got to draw any function. So how do I do that? Well, let's see here. I'm going to draw an axis first. And we're all about x equals 5, so we'll extend this way out there. And there's x equals 5. Alright, so I got to satisfy my 3 conditions here for this function. Now the first thing is f of 5 equals 2. That's just function notation. That's telling us a point. When your x value is 5, your y is 2. Alright, so let's see here. We'll go with 1, 2. So when x is 5, y is 2. That's just a point. There we go. So there's 1. Now, the next part it says, as we approach 5 from the right hand side, that's what that plus sign means, we get to negative 2. It approaches negative 2. Alright, so I'm going to be down to my y-axis here a little bit. There's a minus 1, and let's go with a minus 2. Now it approaches 5 from the right hand side, so I'm going to have an open circle here. Alright, now it could be any function. It doesn't matter what I do. I just have to, as we approach 5 from the right hand side, I just have to get to this spot. So I'm going to say my function does this. There we go.